Okay, pre-calc students, this is Unit 9, Day 1, an Introduction to Limits. Our definition of limit is written here. The limit of f of x as x approaches a equals L. And you can see this graphically on the right. So you can see that as our x values are approaching a, see here's a, we can approach a from the left and we can approach a from the right. Our y values are approaching L. So that's all we're saying. We're saying as our x gets close to a, our y is getting close to L. You can see that with an actual function below here. You can see the function f of x equals x plus 3. So we're trying to find the limit as x approaches 3 of x plus 3. So you can see this graphically. Here's 3, 1, 2, 3, and your point is around here. So you can approach 3 from the left, you can approach 3 from the right, but either way, you're going to get this value over here. It's a little hard to read that value from the graph, but we can see it from the table of values as well. Over here, my x values are getting closer and closer to 3, both from below 3 and from above 3. And as that happens, my y values are getting closer and closer to 6. So we can say that as the x values approach 3 for the function f of x, the y values approach 6, and they actually reach 6. And this is how we would write that in limit notation. We would write the limit of x plus 3 as x approaches 3 equals 6. Now we have another function that graphically looks very similar to the first function. G of x equals x squared minus 3 over x squared minus 9 over x minus 3. And you can see the table of values looks very similar and the graph looks very similar, but this error in the table of values is because of the hole that's in the graph over here. So if you think back to our rational unit, you'll remember that we could factor our numerator and our denominator. So we have x minus 3, x plus 3. The denominator stays x minus 3, and now you can see that these would cancel out, creating the hole that you have at x equals 3. So in this case, our x values are still getting really close to 3, and our y values are getting really close to 6. And it's okay that they never actually get to 6, as long as we're getting really close to 6 as we approach from the left and as we approach from the right. So still, the limit as x approaches 3 equals 6. So this is important, that the limit of the function need not be a defined value of the function, which means the hole is okay. Alright, let's look at this example here. In this example, you can see it's a piecewise function with a few different pieces. We're going to look at the limit of f of x as x approaches negative 5. So negative 5 is back here, and I'm going to go up to the function. I'm talking about this area over here. So I'm going to approach negative 5 from the left. I'm going to approach negative 5 from the right. Either way, I'm approaching this value over here, which seems to be a value of 4. Now we're going to look at the limit of f of x as x approaches 2. So I can look where x is 2, that's right here, and I go up to the graph and I see that there's a hole, and I see there's also a dot there. So what I'm going to do is I'm going to approach 2 from the left, meaning from 2, go a little bit to the left, and now get closer and closer to 2. And I'm going to do the same thing on the right side. From 2, I'm going to go over to the right, and I'm going to approach 2, get closer and closer to 2, and you can see this is the value we're getting close to. It's not that dot. That dot has nothing to do with the rest of the function. So this is the value we're getting close to, and if we go over, we can see that's a y value of about 3. So the limit of f of x as x approaches 2 is 3. That's entirely different from this defined point right here. This defined point is saying, well, if you actually plug 2 into the function f of 2, you would get this output of 5. The limit, though, is 3. Alright, let's look at C. In C, we have f of x approaching 0. I'm going to switch colors because I'm running out of space here. So, as I approach 0, 0 is down here, I can approach it from the left, and it looks like my y values are getting really close to 0. But if I want to approach it from the right, it looks like my y values are getting really close to 8. It's not the same number. I'm not approaching the same value from the left as I am from the right. And so for this reason, we can say the limit does not exist. And in example D, we are going to change colors one more time, and we're approaching 4. So 4 is down here. I'm going to approach 4 from the left. I'm going to approach 4 from the right, and they both seem to be converging on the same y value, which is 0. So this answer is 0. All right, before we turn the page, I want to consider this part C again. What if we just approached 0 from the left, or if we just approached 0 from the right? Then we could have an answer. So let's do a question E. In question E, we're going to find the limit of f of x as x approaches 0 from the left. When you write from the left in a limit, you write a little negative sign after the number. So that's not negative 0, that's approaching 0 from the left. So here's 0. I'm going to approach 0 from the left, and because it's only a one-sided limit, I can now say that my answer is 0. I can ask the same question approaching 0 from the right. So that would be the limit of f of x as x approaches 0 from the right. So I'm going to go to the right of 0, land on my function, and get close, close, close to 0, and look at it looks like I'm getting close to 8. So my right-hand limit is 8. And I wanted to show you that before I show you the formal definition of left-hand limit and right-hand limit, because that's kind of wordy. So let's turn the page. So on the next page, we have the formal definition of left-hand limit and right-hand limit. I'm going to write left-hand limit here. The left-hand limit of f of x. And down here, I'm going to write the right-hand limit. Okay, and if you would like to, you can pause the video and read this entire box, but I'm going to tell you, I'm going to summarize it right now for you. It says that you can approach a value from the left, and if you want to do that, you would write this, x approaches a and then negative after it. That's just approaching it from the left and not worrying about the right side. You can also approach a value from the right. So as x approaches a value from the right, you would put the plus sign after it. And either one of those could give you an output value, which is a y. So in the next example, we're going to see left-hand limits and right-hand limits. We have the limit of the absolute value of x divided by x as x approaches 0. So you can type that in a calculator, and you can see from the table of values as the x's get closer and closer to 0, both from the left and from the right, you have values. But when x equals 0, there's an error. And on your calculator, they don't show you the holes, so you can draw them in to remind yourself that there are holes here because this function is not defined at 0. So as x approaches 0 from the left, here's 0. As I approach from the left, my y values are negative 1. So we'll say the limit of f of x as x approaches 0 from the left, that's this negative sign right here, that equals negative 1. And we can talk about the right-hand limit. So the right-hand limit is as x approaches 0 from the right. The limit of f of x as x approaches 0 from the right is positive 1. So in the box, they're telling you that the limit as x approaches a number can be L if and only if, that's this arrow right here, if and only if the left-hand limit equals L and the right-hand limit equals L, meaning they have to equal the same number. So because the limits are not the same value, we can say that this limit of absolute value of x over x as x approaches 0 does not exist. Let's look at problem 3. Okay, in problem 3 we're going to be finding some left-hand limits and right-hand limits. So first I'm going to find the limit of g of x as x approaches 2 from the left. So here's 2. I'm going to approach 2 from the left, and it looks like I'm getting really close to this y value here of 3. It's okay that there's a hole there, that doesn't matter. I'm getting really, really close to the y value of 3. So this answer is 3. And then in B, I'm going to approach 2 from the right. Well, here's 2, but if I want to go to the right of 2, I'm on this piece down here. So I'm going to approach 2 from the right, and I'm getting really, really close to this y value of 1. So this answer is 1. So the limit of g of x as x approaches 2 does not exist because we're approaching 3 from the left and 1 from the right. That's not the same number. So you can write D and E does not exist. Okay, now let's look at 5. So 5 is down here, right here. The limit of g of x as x approaches 5 from the left. So here's 5, go to the left of 5. We're approaching 5 from the left, and we're approaching this y value, which is 2. The limit of g of x as x approaches 5 from the right. So we're to the right of 5, and we're approaching 5, and it's the same y value of 2. So because the limit from the left equals the limit from the right, we can say the limit of g of x as x approaches 5 is 2. And this dot down here has nothing to do with the limit. That dot is the defined value f of 5, but it is not the limit. Okay, let's turn the page. Now we're going to talk about infinite limits. Infinite limits are a special case of does not exist. So when your graph goes to infinity, instead of saying does not exist, we're going to say that the limit is infinity. It's good to know in the back of your head that this limit does not exist, but the best answer to write is to write infinity because it's a special case. The limit can also equal negative infinity. So in our first example, we have the rational function x plus 2 over x minus 3, and you'll remember that that's going to have asymptotes at x equals 2 and y equals 1. So as x approaches 3, we're getting really, really close to this asymptote here. On the left side, you can see that our graph is going to negative infinity, and on the right side, you can see our graph is going to positive infinity. So we write the limit. I'm going to call this function f of x. So the limit of f of x as x approaches 3 from the left. Here we are approaching 3 from the left, it's negative infinity. And the limit of f of x as x approaches 3 from the right, that's over here, I'm on the right of 3 and I'm approaching 3. This is positive infinity. So does the limit exist? Well, the left side does not match the right side, so we're going to say does not exist. And in this box, once again, we're saying that if the limit from the left equals the limit from the right, then the limit can equal that value, it can exist. Here's another rational function. This time the left-hand limit is going to positive infinity and the right-hand limit is also going to positive infinity. So let's practice writing that one more time. The limit, I'm going to call this function g of x. The limit of g of x as x approaches 0 from the left equals positive infinity, and the limit of g of x as x approaches 0 from the right is also positive infinity. So the question says, does the limit exist? Well, the limit is infinity. And remember that that's a special case of does not exist. But infinity is a better answer than does not exist. So I'm going to stop the video here and let you go on to the second video for the next part of